So we had the problem the last time that our sockets didn't work properly. So when we started it, the package sent back from the server to the client did not arrive. So when we send it here, it didn't work. The reason for that was that we forgot to properly set up the socket for an incoming connection. So here we needed to give to the socket the address of the other connection end, and also here we did not set the right socket, so we were just sending we were sending garbage at at a non-existing socket. Now this is fixed and it works, so when we run it, we will see that we get the connection and the communication goes in both ways. Now what is still missing, of course, is some mechanism to resend lost packages and to try to optimize the available bandwidth for the communication. So we will do that today, and I hope that we will be able to finish the project today. We will see how far we go, but at least for the basics there is not much missing. We have a few not yet implemented opcodes, but that is a good opportunity for some homework. And if there still are no questions, then we will start with some implementation for the data acknowledgement package. So this we have not yet finished. We can, for test reasons, just put some code here on which we can put a breakpoint, and when we run it, we should see that we will receive an acknowledgement package. Actually, two of them for each communication direction once. So once here and once there. And of course, at this point, we still have the data in the buffer. So actually, what we could try is on this side, the client sends data. We could add the sending in the loop and just send a lot of packages all the time, such that we will fill up the send buffer. So we could, but I'm just seeing that we here also may not have the receive right. Well, we should think. No, we have a break, so that will be fine. So let's remove the break. Then the client will keep sending data all the time, and at some point this will start failing. So if this is lower equals 0, then break, and let's print f client buffer full. Client, wait, test client, yes. This we actually are not using, so we can comment. Should we comment it out? Yeah, we can leave it in. We have one send here. Yeah, that looks reasonable. Send buffer, then we send the thing which we received, and then receive again. Now let's do it differently. Let's comment everything out. Oops. And then just run this in an endless loop. So and this thing here, just leave a comment out. So yep, let's see if it works as expected. Okay, we don't want the breakpoint. Yeah, it was too quick. I think we set the buffer size rather low, so let's change that. TCP socket here. Send max buffer. Well, we sent one. Well, 8 segments. We should be able to send 8 packages out. Why doesn't this work? Let's quickly test that as well. So we send one package and we try to send the other package, and it seems that we get very quickly a server full, although of course we could have sent a couple of those. So let's count how many packages we actually sent and add this to our message. Client buffer full after sending %d. So let's see how many this will be, but it's possible that it's not too many. Let's restart this. Okay, so actually this works quite nice. We can send a lot of packages before this fails, but of course since we are not acknowledging packages on the server side, we will never send out the next package. So let's work on this. Sit here. We will need to do something. So let's see. Let's add the process function. Process block. Let's make a just process egg function, which will need just the sequence number, and I don't think we'll need anything else. Yeah, we don't really care for all the additional data which we have in the header, so let's quickly send egg package process and and for reasons of symmetry, let's use this name. Send egg package, process egg package. Okay. So we have the sequence number. We might want to read more parameters later on from this, but for now this is fine. Well, or we pass the whole package as is, but that's something we can change later. For now, let's go with this design since we use this for a process block as well. Okay, so we check whether the sequence number is null. And if it is null, we don't need to do anything except trying to send some more data later on. So actually, I will just leave this empty. In the else case, when it is not null, we will need to mark the right package as acknowledged. So we will look if we can find it. So auto e ist gleich m send buffer, find int max minus sequence number, since for the other buffer we used a different order. Genau, and if this is not end, and then we found it. We don't really need an explicit else case if we don't find anything, because if we don't find anything, we just silently ignore that scenario. This is for later, so we can now we should check, of course, if we have sent the package at least once. I mean, this is not a situation which should happen, but could be for whatever reason. Yeah, but we don't have yet anything where we would complain about such things. So, well, if let's put it here. So if it's not null and send is greater equals 1, so it was sent at least once. Now if it is 1, so if it's sent once, then everything is fine. If it was sent more than once, then it means that we had some package loss. in which case we will need to um, change something with how many packets we are sending out per unit time. Okay, so if it was 1, we can do a few things. So we had here this send time, which we filled with. Oh, we did not fill that in. That is, of course, not good. We should fill the value in. Where do we set it to 1? Have we forgot to set send count to something? That would be well possible. Yes, we forgot that as well. Okay, so there are a few things missing. Send block. So if we have a block, then we set the sequence number, the package, and in the block itself we will need to set send count. Well, we increment this and block set send time. Or did we choose here ulong? Let's be on the safe side. We don't have this defined. Okay. What was it? Get the count. Get the count 64. Okay, they use ulong, which is pretty much the same. Okay. So now we have those information stored. And of course, if we resend the package, then this would change. But we would not know once the package is received and we get the acknowledgement for which of those packages arrived. So we will evaluate send time only if send is set to 1 and we know that this is reliable. So we have our send time. We know that it must be. I don't think we will need an else case here. We will see. So we should also check here, just on the safe side, that now this would get the count. So we check that time is smaller or equals current tick, because so the get tick count counts the milliseconds since the operating system booted, and in the 32-bit version of the function you will get a wraparound, so the value will reset to 0 after 44 days. If you use the 64-bit counter, then it's pretty sure your computer will never run so long. Probably our civilization will not last so long before that will wrap around. So that's why we change it further up to a 64-bit counter. Although actually we could count so 44 days times 4, 1, 2, 3, 1, 2, 3, 1, 2, 3 divided by 3, 6 that is many years before it will wrap around. Did I not? No, the amount of zeros is right. Yeah, 4 billion. So yeah, this is definitely a safe bet. And press the wrong button. I hear some noise. Someone should turn off their microphone. Wait, I can do that remotely. Stumm schalten, mal stumm schalten. Huh? Stumm schalten. Yay, the noise is gone. Very good. So where were we? Okay, yeah, so we know now that this calculation will be correct, so we subtract those, and this gives us the round trip time. Well, maybe we should do it later. For now, let's just go with sample round trip time. Okay, now there are two scenarios. Okay, this will be a to do for later. Calculate an average round trip time. Okay, and we are happy with this part. So we have here the to do for later. And for the rest, sound count is 1. We don't care about the rest. Yes, now we want to remove the package from the buffer. I mean, in principle, we should go with this structure. Oops. Okay, so oops, buffer erase I. So the package was set, it can be removed, and we will need from our m pending window size minus is equals, was that 1 or was that the size? Okay, it was just the package count. We did not use the actual size in bytes for this. Okay, so we did this. The upload buffer needs to be reduced as well. Oops. What was it? Send buffer size minus is equals that's a mistake. We need to delete the element once we are done using it, and we will need something from it. Second size. And another issue, we need to delete it since it is created on the heap. Just looking, did we use new or did we use okay, we used new, so it's fine. We can delete it and then we can erase it. Do we need anything else from it? So this and this deleted it is. So then we can now try to send the next package if there is one. So in any case, try to send. Okay, and try to send just try to send as many packages as we can to fit in the pending window size, which for now is still only 1. And we will also need to do a different thing. That's a to do for later. Okay, so this should already be working. So let's try running our program, and we should just get an arbitrary long amount of the same message being printed over and over and over again without any error. Okay, something failed miserably, but it was at least working for a few packages. Let's see what's wrong. Call stack. Okay. Receive buffer is 1000 and this is more than 1000. Okay, it's just too much data, so let's just go here with -1 and make this by 1 bigger, because that's can happen. So what happened now was we were so infrequently querying the buffer that once we did it, we got more data that, well, we got the buffer full, but we tried to always set the last character to 0, which meant we accessed one element too much. So this will not happen now, since we claim there is less, and well, there is no crash, but it still is not running all the time. It now looks like a synchronization error, so at some point we just run into a deadlock somewhere. That will need to be improved. Let's see. test client. Okay, assuming this happens, where are we hanging? Okay, so this one hangs, of course, but within our socket process. Okay, so this part works. So the client somewhere hangs in the sending. I know what happened. We just that's not enough. But I guess we filled the buffer, but then it should write this message. I think there is a bug with the... no, it wrote the message, so but the amount of packages is wrong. Okay, that needs some improvement. So one thing, let's try not to... just write the... let's just sleep. Oops, and write the message. And then we will see if it at least runs forever without hanging anywhere. Okay, now it always claims the buffer is full, so something is clearly broken with the receiving section. So let's see. Here we have our test server pods. Okay, so let's put a we want to go here. Let's put a breakpoint here and see what's the state of our client. So we have the client, we have our member variables. Receive buffer. Well, the receive buffer, this side claims it's 0. But it also is supposed to send everything back. So what we could do for now to simplify it, we can turn this off. We only want the server to print whatever it receives, and we want the client to just send the same thing over and over and over again. But as said, this will still at some point run into an issue. Yeah. Again, let's see here, client. Send buffer 0, receive buffer 0. It claims it doesn't have any data, and if we now look for on the client side, then it will say that the send buffer is full, probably. Send buffer contains 9 elements. So it seems we have a problem somewhere here. Let's see what the send function does. So it checks and then it will try to add blocks and put them together. One thing we could do for now is we could comment out the part which is supposed to add data to the end of the block. Yeah, so if block is null, so basically we just don't care for we don't care for finding the block. Sequence number, but we need to this is not yeah, basically we just need this part here. Okay, and then it will always go into this case, so I can put a... let's comment this out. Stay on the safe side. Okay, and let's run it again. Let's see if this improves the behavior. For now, okay, this is saying let's try again. Okay, so this works fine. When we don't try to merge packages, this works as expected. So something is probably wrong with the package merging code. So let's take a look on that. So size must be small and send count must be 0. Then we can reuse the block or else here. Create new block. Yeah. So let's put a breakpoint here and see what will be the problem. Okay. So we have a block. We will check again that it definitely was not yet sent. So these two are really 0. And then we add this to the send buffer size. Size is the amount. Well, we change size here. That's the bug. That's a bug. What is it? Size? No, it's not. You only take a portion of size. We increase. Okay, and we copy. No, that's fine. That might need some more debugging. Then we do try send. We have checked that we definitely set those. Yes, we do. It can of course be also some sort of synchronization issue, but we should be locked when we are here. We should be locked when we lock this anywhere? Yes, we have the lock here. If we process the egg package, are we locked there? That could also be that this is not. Sorry, process egg package. This comes from process package and doesn't look like we have a lock there anywhere. No, sorry, we have the lock here at the top, so it should not be a synchronization issue. Okay, so let's just add some debug information that we can see what is happening. So let's define some helper function which will allow us to print verbose debug output somewhere. I don't know, maybe here. GCP trace. Do we need? Well, and we need the address as well, so we need a few things. So let's take void socket. The address. Actually, we could move it down, and then we could take data and address from the thing. So let's put it here. A tracing function, which will take just a socket, and then some event ID, or maybe let's do it even simpler. We will just print text and nothing else. Oops. Can then think about making this more elaborate. So we need to include hash include for this one. Okay, so for list line buffer, comma, buffer size, comma, point, and we should use maybe size of, okay, okay, so this prints us the variable argument path, and then we will make an on printf. Trace %p comma socket, so that we know which one is which, and then printf %s, oops, %s line buff and \n socket p double, yeah. Good. So do we have any trace? Yeah, we had already some traces here. So let's go with starting by replacing those. So when trace is this, yeah, this, comma, connected. Don't have, okay, we don't have any other. Okay, so actually we should call it Synac received. Then for blocks, yeah, for now we will also need blocks. Data, acknowledged. Okay, let's run it and see what we will see. Okay, we forgot to add a trace to the send, and also it's complaining about something. Yes. Properties. Let's see. So the typical string operation functions which don't take the string length as an additional security parameter are not supposed to be used anymore for security reasons, obviously, but you can disable this safety mechanism by adding that preprocessor definition. But we said that we forgot to send at least some. Okay, and we didn't say what was happening, so let's improve on that as well. Let's Synac data arc, and then we have some of our send data package, send reset. Okay, this we can add here as well. Send send Synac accept connect to receive send try send block send data process block send data. Okay, let's run. Okay, so we have a connection, we send data. This thing already complains about the buffer being full. We receive a Synac and receive a couple, and then we again complain. Okay, so we'll need some more tracing entries. So here we have send. We don't care for the error case. Here sync accent. New send append, so we know what's happening here, and receive. If somebody was it already here? A process block. Here, if we have something, then we'll add here just receive. It seems we're either dropping sometimes a package while starting up, or we have some other bug that sometimes prevents us from connecting. Okay, interesting. Just added trace messages and it's completely broken. So we might need to debug that right now. Presumably this just some timing issue. So by adding the additional trace messages, we change the timing of the thing. Okay, we don't have here, so we should add here a trace entry send sync. We'll send sync 1, and we have the other place where we send that same package. And we sync ACK. Do we have only one? Yes, we have only one. Okay, then let's see. Let's add a delay. Perhaps the server is not yet up and running, so let's just add sleep. I don't know, 500 should be enough. That should solve the issue. Huh? That is strange. Where we get in? Oh, the trace is broken. Why is that? Why doesn't this like that? That should be normally working. Yeah, this is defined on that. I mean, we can also go with %. Rule 8. No, that's more. How many? Okay. How did I break this? That is strange. Normally printf should always work from anywhere. We'll just close that helper window and rerun everything. Yeah, now it's working. Weird. But then this $%p should still work as well. So let's just run it again. I guess there was something broken with this helper window here. Since it's a continuously running process, it must have locked up for some reason which we did not cause. Okay, but this seems to be running now all the time without issues. Send append, send append, send append, then this works as well. We get new. Okay. So what we now can do is we can just, if we don't want the debug output, just return at the beginning of this function, and we'll get only the output from our test client code. But now it is blocked. It doesn't seem to be doing anything. Test client. The test client is trying to send something all the time, but it is not succeeding in doing so. And the send buffer is full. We have 8 packages in it. This is what we expect. And on the server side, however, the client says that the receiving buffer is empty. I mean, it can of course be that we already now get a packet lost. That but I would not expect this to happen when we just connect to localhost. So normally there you have as much bandwidth as you want. What can we do to improve that? We could add a delay so that this here always makes a delay before it sends the next package. That would be good for initial testing at least. Yeah, that seems to be working fine. Is it still working? Yes. Okay. So perhaps it's already now package lost. So in this case we can, or maybe let's leave it for now as it is, and we just add later some controlled package lost before we do that. But what we then, what this means now is we really need to add the mechanism to resend packages in case they have been lost. So to do this, we already have a thread somewhere. Thread process, yeah, this one, socket process, which runs all the time. That will also need some improving. Let's put a breakpoint here. We should run here often into the error. Is that blocking? It should not always be blocking. 27. Well, yeah, okay, that we should at least run it as 0 case. So let's, if this is 0, okay, let's that case we should reach often, since we have now this delay, so there should not be that many packages moving. No, but we don't, so that would mean that it's always blocking, that this receive is always blocking. Okay. We could enable the socket to be non-blocking, but actually the problem is, if it's always blocking, then we cannot use this thread for some sort of timer based timeout. So we will need to enable the sockets which we are using now to be non-blocking. We always create it here, so we will also make it non-blocking here. EO get comma okay, so now our sockets, all our socket operations will be non-blocking. So we should check whether we are happy with this. So here we assign it, close socket is fine. Bind is always instant. Okay, receive from will be non-blocking, so it will, but I think it will return an error actually here. Let's put a breakpoint instead of 0. Okay, we send, and then we actually don't care for the send to finish, so this is fine, this is fine, this is fine. I claim it's fine. Let's see if I'm right. Yeah, and we have here the arrow VSA would block. Yep, it's this one. So if it's VSA would block, then we sleep and continue later, and later also we will have some timer, some additional timer somewhere here, but now we at least have the loop spinning all the time. 10 milliseconds sleep is enough for the loop to not create any larger amount of CPU usage. We can quickly take a look on that. TCP. So as you see, we are not using too much CPU. Okay, so let's stop that. And let's add a controlled package loss to the mechanism. So when we send, was it send block here? Yeah, if rand modulo 10 is equals 0, then just return. So that we don't forget to remove it later. So this will cause, for now, the mechanism to break in a similar way as we have seen that before. Okay, now it broke at the very beginning, so this is not good. It should only happen when we send. Wait, modulo is equal 0. But what is the chance that the first thing is already a multiple of 10? Let's go with 1%. That should then be changed in the comment as well. And to rebuild that. Yeah. Okay, well, it still was not really 1%, but after 3 packages it broke. And in principle, now it should always break after a couple packages. So now we can add the resend mechanism. We have our socket. Where would we want to check the resend? So one good strategy would be to add another variable where we count the time passed. That's on the sending side, or let's do it somewhere in the general state. So standard pods, we initialize this to 0. Address socket will be quite with our endless loop. We will also need to think later about a way to terminate it. But if okay, so if get tick count minus get timer pros is larger than let's say 100, we will check 10 times per second if we need to resend something. So this is M. Is that the best scenario? Yeah, it's good enough. Well, technically we should do it on a per socket basis, so for every individual socket, but we have so many, and since it's the same value, we will just keep it here for now. Okay, so then if this is the case, then we can of course update our variable, and now we will need to in a loop for all our sockets where we have them socket map. Oh wait, that will depend on a few other things. M as state. What values did we have? I think we had a dedicated listening. Yes, listening value. So if state is listening, then one case, else is the other case. So when we are here the listening the implementation of the listening socket, then we have a lot of individual sockets for which we need to do it. Begin is like end I plus plus I second process timer, and if we are not a listening socket, then we are, well, our own boss, so to say, in which case we just go with this process timer. We will of course need to add this function somewhere. Process timer. Okay. Okay, yeah. So we will need to lock our own object for now. That might be something we might need to do. Socket map. Yeah, each time we access socket map, we should lock our locking critical section. Although, let's see from where we access socket map. We definitely need a lock for the new socket since we access this from outside. But just socket map might be only accessed from this particular loop, in which case we don't need a lock. Yes, it looks like we don't need it. So if we are not accessing it from outside, it's fine. So let's go with this like this, and then here we will be locking each individual socket internally. So let's check our upload buffer. So for auto e is equals m send buffer. We should go from the back to the beginning. So reverse begin e is not equals punct end. Actually, this should be a plus plus I, because this has better performance. Okay. So if it was never, if this, so now we will be going from this side of the, so like we are sending from one end of the buffer, and we will process the buffer from the same side. So as soon as we find an entry which has send count 0, then it means that no more entries in the buffer can have it non-zero, since we are sending from one side. So then we can break instantly. This is a nice optimization. And I said I will try to comment more what we are doing and why we are doing it. So the last time, so here hence okay, and let's quickly check if that's true. I think it was try to send again. Try to send. Fine. Okay, yeah, that we are going by this by the sequence numbers, but that should have the same result. We can actually we could put a breakpoint here, and see if this works. If this is wrong, let's quickly run that then. Yes, so we have buffer with one item that's boring. Okay, it's kind of a boring case. Now we broke, so now we have more than one entry, and the first one is not sent, and the second one so it's from the back, so the second one is sent, the first one is not sent. So this seems to be working correctly. Yes. So second send time plus we will need some timeout value. We will need some timeout value. Let's put it somewhere on our M object. So send buffer long. Let's call that short timeout or no, packet block timeout. That sounds nice. We will later have to, of course, think about finding a dynamic way to calculate this timeout, depending on the network behavior. But for now, we will just wait, no, it was here, I think. We will just pick a value. Let's say 1 second. Let's say 3 seconds. If a package, yeah, 3 seconds. If a package was not acknowledged within 3 seconds, then we will assume that it is lost. Okay, so if this is equals, and we should also get the current tick. since we will need it. I mean, if you would really want to optimize everything to the max, we could pass this value here as an argument. Why not? Why not? We only save very little, but every bit of computing time saved is good. So okay, if this is so the time when it was sent plus the timeout, so this puts the value, the sum here, into the future, and if this future is still smaller than the current date, so if the future lies in the past, this means that the timeout was exceeded. So then we will check how often the package was dropped. Oops, what did this happen here? If okay, maybe we should try to make the code more readable. So we will always, from now on and I will later refactor the code, assign the I second to a variable called block, because this makes everything much more readable, I think. So if block send count is greater than yeah, let's take a max of 3 and m. Did we define it already? Have a pending window size, but that is not the same thing as what we want. So let's define another variable. Wait, did we only have? Okay, we already have the variable. It's just called window size. Okay, so if this is bigger than 3 or window size. Okay. So the idea of this window size, I think I have not explained that yet in the past, since we had other more pressing things to look into. But since we are now doing the resend and retransmission part, we should maybe talk a little bit about how this is supposed to work. So the idea is when we start the communication, we will set the window size normally to something low, like 1. We will just send one package, we'll get an acknowledgement for the package, and then we will increase our window size by 2. So this means that the next time we are sending packages, we can send 2 packages. So the window size describes the amount of packages that can be on their route to the destination, which are not yet acknowledged. So for example, if it would be sent to 10, then we could send out 10 packages without waiting for an acknowledgement, and only for the 11th package wait to get some of the already sent packages acknowledged. And the mechanism later will be such that each time we send packages out and receive acknowledgement, we will increase the allowed window size by 1. And as soon as we run into a packet loss, we will divide the value by 2. So well, I don't have anything to draw. MS Paint. Let's try to make a really shitty drawing using Paint. So if we have, well, package count is the y-axis, package window size is the x-axis, then it will look something like we start at 1, it goes up, and then it falls down to the half, and then it then it will repeat this behavior. Of course, if then we have more bandwidth, then at some point might grow higher, or if we then have too much okay, let me try to make it nicer. And then if we at some point have too much package loss, then it will grow smaller. And this mechanism is pretty much how the TCP protocol also manages its own sending window size. So we will try to emulate that. Okay, so if the package was dropped too often, then at this point we should consider the connection lost. Do we want to wait for anything else? Not really. Send. Do we have a send reset? Yes. We send a reset package to as a address. I think we need to take reference on that. And we will need to set the connection as broken. This is also important. M status state. Okay, then state not status. Well, we don't have any of those states, so let's just add another one. Broken. And state is equals connection is broken. And we should of course trace these as well. Okay, we have sent reset. Then let's just add a comment that too many send failed. Too many. Let's make a nice text for the error message. Okay, so we have this, and then in principle we can return from this function already. I'm thinking if we want to add some sort of additional delay. Yeah, I think there is no point in waiting. It's just that semicolon. Okay, so this is the case if too many were lost, and if not too many were lost, then we will now need to do this, but this is a to do for later. So we reduce the buffers, and we can we do that always? Well, the package was timed out, but we still need to resend it, so we just go with try send. What was it? Try to send. Since I said we need to at least resend those packages at some point. We should reset something so that we can resend it. Okay, so this must be null. That is definitely true. But I think we will really need to, because in the try send we are checking. No, but we are just taking a package from the queue. That might be a problem as well. We are not checking what we are taking. We should only take packages which have not yet been sent. So we will need to improve on that. Well, but we can do different. We can let's improve that. So first of all, when we send it, send block here, we increase this and we send it is fine. Okay, so what we can do, which is definitely easy, is we just use send block here. Then we just pass the block which we decided we want to resend, but in this case, yeah, if the timeout occurs and we don't break the connection, then we can just resend the block outright. We will not be waiting with the resend for the window size to be reduced. Yes, we will only slow down the sending of new packages. That is a valid approach. And what we also should do is that if we don't have a timeout, but the block has been resent more than once, as one, then we should break this loop and not try to resend more than one package at a time for now. Break. So good. This is then we need that's a to do for later. Do we need anything else? Yes, that's something for later, but we will already implement now. So if wait, since we have not yet implemented that part. Okay, then we will not do it. So if something and oops and so this will be oops flood. So it was just send buffer size is not null. Then was it send block with yes so this will be something for later, just that we don't forget to do that. Yeah, let's put a breakpoint here, but in principle they should be working. So we from time to time check if we have a package missing. If it is missing, then we send it. Let's do this. Let's drop packages randomly only if this is 1, so that we always know that the resend will work. For our testing, this is a valid simplification. So if we have a block, well, if the block is defined, then we increase this and we set that. Yeah. Should be working. Let's try. Okay, something's broken again. Let's just... Or we are running in an endless loop somewhere. That would also be. But let's just close all the helper windows and restart it. Yeah. Okay, so yeah, it's working. As you see, so it broke. Then it well waited. Now it's still sending successfully. At some point it should, however, run into a okay, now it ran into again a packet loss. It's resending, so each time it runs into a packet loss, it waits for some time, for the 3 seconds or to 1 second, however much we set, and then it repeats and continues. So at this point we already have a connection mechanism which is reliable. So we know that if some package is lost, then it will be retransmitted, or the whole connection will be discarded as broken. What we now are missing is some code to set the broken state if we receive the reset package. So that we will add as well, and then we can start looking. Well, that we have still to debug why while merging the buffers didn't work. So this is one thing. But the other thing which we will be able to do is we will be able to now to look onto this so-called congestion control algorithm, which is how the amount of packages which can be on the route is scheduled. So what I already showed you in the paint drawing, how TCP does it, and we could in principle try thinking if we can somehow improve that. Since of course TCP was developed very long time ago with very slow connections in mind, so perhaps if we think about modern 10 gigabit connections, we could come up with some strategy which would still not block too much the network in case of congestion, but at the same time allow for higher data rates. It sounds like a fun little endeavor. So let's quickly check this as 10. Okay, so in this case, so we receive reset. And this already on the thingy, so we just set the state to this equals broken. Yeah. Okay, since we have already our trace, we could add this as well. So package opcode. So here we can add a nice error message. Yes. Good. So we have this. This thing is still for later. This will be the homework. So as we have described somewhere here, here, the operation plan of our protocol is the client, or the connecting party sends a sync package. It receives a sync acknowledgement. It sends its own sync acknowledgement, so it's a three-way handshake, and then we start sending data in both directions as much as we want, each time acknowledged with an data egg. And at some point, if we want to close the connection, we want to do it gracefully, so we don't want just to stop sending data and let the other party wait in a endless timeout or anything. We really want to say we are done, bye, see you later, alligator. And we are doing this with this finish or fin package. And here this connection is done also in the shape of a three-way transaction. So we send that we want to close the connection, and the other end says okay, connection will be closed, and then we acknowledge this again to the other side that the connection has been closed. The last acknowledgement is probably not really so important, but as far as I remember, TCP does this way, so we will just stick to it. And the homework of today will be to implement the functions for this. So if we go somewhere down to our close socket, this will do a well, first let's quickly show me. Let's quickly find the send. So we will need a couple things from here, this and this. Okay, so of course we need to check whether so first of all we need to lock the object, then we need to check whether we actually were connected, because if we were not, then there is no point in disconnecting, and if we were connected, then we can send in, how they call that, send. We don't have a send ACK, we only have a send send ACK, send package. So let's just say that we will send it from here, some to do 17 11 20 22 a send a this thing does not have any particular arguments, so when we look again on our block structure here, it's just protocol ID, which we already set, our opcode, and here we don't need to fill in anything. Okay, so this is 1, oops, 2, implement, well, we don't need any process function in this sense, since it's quite trivial. So this one and this one, implement handling, implement for TCP. This means set to disconnecting, yeah, set, yeah, then 3, yeah, 3, implement, okay, wait, two things, send, wait, set to disconnecting, send the ACK package, disconnecting, send ACK package, okay, implement handling for ACK package, set m state to disconnected, and no, if state is not disconnecting, then send ACK, then send state to disconnected, and then the other end, and then the same package is then received by the other end. It checks whether it is disconnecting, and since it sees that it is disconnecting, then it doesn't do anything except setting state to disconnected. Should work without any disconnected 1, 2 or any other more complicated thingies. Yes. Now, of course, at this point we are still missing some logic to later clean up things and stuff like that, but that will be something for later. Okay, so we have homework, and I think, since, as I mentioned many times, we are supposed to make a 15-minute break during this longer lecture, I think this is a good time to make a 15 minutes break. So let's say until 16:40, and if you have any questions, you can ask them now, or you can go on a break. and ask the questions later, or just use the break to think of questions which you will ask later. As you hear, I like questions. Okay, so if there are no questions, I'll turn off my mic for the 15 minutes and we'll see each other shortly. Mm-hmm. Yes. Um. Yeah. Well, that's the that's the challenge, isn't it? Um. So my suggestion would be to just search for algorithms for multiplication of integers, and there are those algorithms described with code examples how to implement such things. Yeah. Okay. Any other questions? Okay, so the break's over. Everyone back? I'm thinking about the finish handshake. Whether this is correct, what I wrote down at the top. Because the way this is done here, we would only have a fin and then an egg, and then we would not acknowledge that, I think, again. So properly, to really be a proper three-way handshake, we first, of course, need to send a fin from one side, set our own state to disconnecting, then we receive the fin flag on the other side. Then we will check if the state well, if we receive the fin, then basically it should always be already well, when we receive it on the other end, we just send it to disconnecting and send the fin acknowledgement. So maybe we quickly open the notepad with and copy our protocol specification. Somewhere on the side. Oops. Okay, so this is what we want. So we'll go back to the specification. Oops. Here, so we start with the fin. So step one, send the package, set the state that we are disconnecting. Now we are here. We need to send a finish flag, and we need to also set disconnecting. And we only then do this if the state was connected, so we can check this. So if state is connected, then we set disconnecting and send an egg, and then on the other end here, when we receive the acknowledge, so when we are at the other end, then we will need to send an own finish acknowledgement, but we don't want to send it twice. So the same issue we had at the beginning with when we were handling the connection, that we needed connect 1 and connect 2 to distinguish the situation. And here, if we get the finish acknowledgement, we don't if we set it in both cases to just disconnecting, then we don't know whether we should reply once more or not. So we will actually need to change this. It will become a bit more complicated. We'll implement disconnecting 1, send fin accent, disconnecting 2, fin and fin accent, and then disconnected fin acc received. So let's revise the plan. So we send a finish flag. We set our own state to disconnected 1. Then on the remote side, we receive the finish opcode. We check whether we actually are connected. If we are connected, then we set the flag to disconnecting 2. Is that correct? Yep. And we send then a finish acknowledgement package to the other side. And the other side receives the finish acknowledgement package. So it checks. So if state is set to 1, then send again a finish acknowledgement, and set state. I think it's still slightly bugged. To disconnected. Wait, there is some condition missing. So we receive and on this end, where we already are not connected, but we still need to set to disconnected. Team. Okay, we can, let's ignore that. So again, restart. And think about the other side. So on the other side, implement opcode von fin. Okay, basically it must be here. So if the state was 1, then we send back and set disconnected, and else if state is 2, then we just set the flag to disconnected and don't send anything back. Is that correct? So we send side A, we can write that down quickly. We have 2 sides, A and B. Side A, send fin, set status D1. Yeah, then side B we receive fin, we set status set D2 and send dingsta boomsta fin ac. Then side A again receives fin ac. Then sets status D. D just means disconnected fully. And it needs to send its own fin ac. And the other side, retzv fin ac und set status D. And now both are disconnected and both are in a defined state. Here we can also change the order, but now let's stick with this order. So send set status D1, maybe like the set status D1, send fin, receive, set status, send, receive, send. Yep, this should be working. So sorry for the confusion earlier, but as you see, it's easy to get to get entangled in something and not think everything through to the end. But now we have a plan for the homework, and now for the last 30 minutes we can spend our time on improving the code that we have already here. For example, we could start with implementing the congestion control. That should not take that long. So let's see what we have. We have window size, we have pending window size. Then we will need to I think we need to have a few more variables for a few presets. This one will be calculated. Okay, so first let's maybe rename those things slightly. Although we need that. Yeah. I think this we should really just call congestion window size. To make everything exact. Okay. That's one thing. What we probably will also want to do is to advertise our window size to the other side, but that we can do later. We change that. Okay, yeah, we need another helper variable. Congestion threshold. So we have congestion window size. Two will be something else. Then we wait, let's do this here. Okay, so to will be advertised window size. So we will later enhance the protocol header that we can tell the other side what window size we have on our end. That will help. We have the congestion threshold, pending window size, and timeout. Maybe we should actually move the timeout here, since the timeout is something that happens before we start messing around with the congestion window thingies. Okay. So congestion threshold. Okay, and pending window size is the block count. On the network. Okay, block timeout is, well, okay, we will need a couple more things. We need a round trip time. That will be a to-do. Estimated round trip time. From packet sent to packet arc to from packet sent to receive an acknowledgement. Genau, estimated and then what also would be good would be to have something that tells us how much this round trip time that we measure here is varying. So we don't want like to only have the latest round trip time from the last package we received, but we want somehow to know that if the network conditions change, how large spread we can expect for this round trip time. So let's call that timeout deviation, and we use large O without here. And we have here block timeout, which we will compute. It is also in milliseconds, and the rest is self-explanatory. What else would we want here? I think nothing, not for now. Here we have this. With that we are happy as well. Okay. think this is for now the most important things. So let's see. We need to initialize this. Oh, did we? Okay, it's already initialized to 1. Congestion threshold is not initialized, so we will need to initialize this. How to, what would be reasonable? Congestion window we initialized to 1, pending window is null, and congestion threshold, let's be send max buffer times 8. Just for now, just initialize it to 8, and we'll think later about changing that. Okay, now let's make a definition for that. Fine. Default well, default condition threshold. Default send buffer 8. Okay, zack. Okay, then we also make a default receive buffer 16. Max segment size. Okay, yeah. Define default max segment size 1300. Okay. Good. That sounds reasonable. Okay, also a default timeout value. 3000 in MS. Bytes count, yeah. Yep. Okay. Advertised window size, that could be added later, or is it now? Let's implement this advertised window size right now. This is an important feature. Let's not wait with that advertised window size. We need to initialize it, of course, again. Wait, do we? What will be the start value for that? Actually, at the very beginning, it will not be. It should be initialized to 1. The same value as we have here. Yes. That sounds good. Okay, so we can go to our package definition header here. We have a union, we have one data. Data would be so it is to be in every egg package, so it needs to be, we need the sequence number, but instead of data we add here a oolong window size, and we call this ACK. Yep. So send oops, damn it. Don't we have a send egg? I thought it was it. Send egg package. Yeah, that is this. How often do we do that? We have it here, here. Yeah, but we can. Okay, not data, but ASCK. Oops. Sequence. Wait. Again, quick look on it. So we have our union. We have our structures. This is not named. It needs to be named. Okay, so ACK sequence number, ACK window size is M, advertised window. Wait, is that correct? No, it's not. That will need to be the congestion window. M. On the sender side, we advertise, I think, the congestion window size. Data egg. Sequence number. No, it's also wrong. Damn it. We need to calculate that. So this will be the count of the count of packages that we can fill into our buffer. Okay, so if m download, no, that's fine. Let's file buffer size is smaller than m. Let's file max. Let's file buffer. Then this is something else. This is 0. And that might also end up being 0. So maybe we want to change it. So so the buffer size is smaller than max buffer. So max buffer minus let's file, and we want to divide this by the segment size. Yeah, m max segment size. We might to make the things more elegant, change the window definition to not be the count of packages, but actually really the bytes in the buffer that we have 3. Yeah, that sounds reasonable. It would be more in line with the original TCP implementation. So maybe we should do that. Yeah. I mean, we can of course cheat around here a bit and use the bytes for what we send over network, but for our internal calculations then just divide it later on. So maybe let's go with this approach. Okay, so we have our window size set, and we tell the other side that we have still room in our buffer. Because what could of course happen is that we receive our package and then the buffer is full and we don't want to receive any more data for now. Okay, so this is fine. This is fine. Then here, of course, this will need to either receive the window size or receive the header. Then we'll also need to change the process block to be elegantly aligned with the rest of it. So in principle, Yeah, it's not the prettiest thing, but let's go just with all the process. Send process. All the process functions will just take the whole block. Or wait, we could improve on that, could we? Because we have everything here, we just need to give those things names. Yeah, we can improve that. So we call it struct data ack, and then we have union data ack, and then we can use these because we don't need unused, we don't need opcode, and we don't need protocol ID for further processing. So we have data and ack, and then it's this p data, then it's this p ack. Okay. Okay, so p. We will need that later. Oops. P data that needs a reference. Okay. This. We called it. Okay, there will be a few more improvements potentially. This should be fine. Yeah. So sequence byte and that should be fine, I think. So sequence number is sequence number. Const byte data is p data data, and size is equals no, we need to add a size parameter explicitly, but that is okay. This is okay. It's the only package that needs that size. Well, yeah. Data comma size. Yep. Okay, so this is fine, and now the other one. Oh wait, what is it complaining here about? Yeah, here we only pass reference on ack. Yep. This thing takes not sequence number, but our. Why did we add struct for here? Yeah, as well as data. So sequence number is null. Oops, if it's null. And then sequence number if it's not null. Yes. Where is it complaining? Here, insert. Why is it complaining now? Block should be fine. We don't have sequence number, we have as well. Huh? Missing a constructor, we didn't change there anything. Long, it should be long. And then here, yeah. Number, sequence number long, I think this should be it. Still complaining sum data. IP data and p data had a different meaning. We have two p datas. That is not good. Do we need this p data anywhere? No, we only have one. So let's just go with this. That was it p data. Yeah. And we could maybe rename that to something. It's an array. Well, it doesn't matter. Okay, so we fixed what we broke, and then we can now continue. So this sends always the most recent congestion window size. Process acknowledgement package. Okay, then we can here add a few improvements to our process package. So, well, if sequence number is nothing, this is just a sort of ping that we send to notify the thing that, so we should probably write this as a comment. Of the new receiving window size. Okay, and we could check whether it's larger 0 and complain if it is 0, but I think we don't really need to be that pedantic at this point. This is for later, close, and then we need somewhere for 9 too much, and then we need somewhere also to send those things. Calculate round trip time, try to shrink. Okay, we had this, this we also have. Yes, so here. So, that was the recent thingy. So if the current advertised window is null, so and buffer size is not null, of the receiving peer. And send buffer size so we sent a block, sent an empty block. Okay, yeah, no, the comment is slightly wrong. We need to ping the receiving peer to get the to get its. Okay, so we send an empty block to it, and then we expect it to answer with an empty acknowledgement package. Process, what do we have it? Send egg package. Process block, yes. So we have process block. Sequence number is 0, and then we send egg package for sequence number 0, which then just contains our new receiving window size if it has changed in the meantime. So if we have called receive and stuff was removed from the buffer, so this got smaller, or maybe we called another function. We don't yet have to increase the buffer size. But in any case, if we got something, then we will do it. And when I think about it, we could, in principle, make it such that if it's 0, then we just don't answer the ping, since we are not expecting it anyways. We could do that. If a sequence number is 0, is 0, then return. Yes. Yep, that makes sense. I think. In theory, you could implement it such that we would be tracing the sequence numbers even if we send some empty pings out, but this is not what we want. I think this approach is good enough. At some point, we'll run into a timeout anyways if we cannot send, if the buffer of the other side will not be cleared in time. Okay. No, we need to improve something else. Okay, so we have the we have not evaluated the window size anywhere. Process egg package, acknowledgement package sequence number, and then we can just read it. So m advertised window size is equals pack window size. Yeah. We are not using this yet anywhere. We are just reading it, so we probably should use it. Can we use it easily without changing too much to the yeah, we can in try to send. So here we had we were checking whether the congestion window size is larger than pending window size, but we will take the minimum value of either congestion window size or advertised window size as our condition. Because while we still may think that that there is enough room to send stuff, and we will not need this up and lower bounds, I think, in the end at all. So it's actually a bit simpler an implementation than anticipated. Okay, yeah, and if we can, as long as we can send, then we will be sending and just always taking. Wait, is that correct? Yeah, because we use the last sequence number. That helps. That simplifies things significantly. Yep. Okay, try send is, I think, quite well done. So we have the send block where we have our trace, we have our synthetic packet loss. Yes. So the way this works now for bandwidth control is that the remote site will tell us the advertising window, and then here we will not send packages to it if the last thing we heard from it is that that site does not have any room to get any more packages. So we actually are not so normally if you would use some sort of bandwidth control with TCP from the receiver side, so as a sender it's easy, you just send at the rate you want, and if you can, then you can. If you cannot, then it will be slower. But managing the bandwidth from the receiving side in TCP is not so great, because the only way you can do it effectively is by not receiving data from the buffer. So you would have something that calculates how many bytes from the buffer per unit time you are allowed to receive, and then you would read the buffer at this rate, and the other side effectively would still try to send you packages, and those packages would be becoming lost. So this is not super great, although of course, because each time one package is lost halves the bandwidth, at which it tries to send, then of course you only need to lose a couple packages to slow the connection significantly. Now here we have our advertising window, which is helpful at least to note that there should not be much more packages sent. So this is somewhat an improvement. But we need to check whether our timer procs function does everything correctly. So we have here, wait, no, that's not the right one. Here, no, damn it. Here, the process timers. So we would of course try to send what's missing. I'm thinking whether we might be able to put ourselves into a situation where we cannot do anything. So here, if we cannot do anything, we of course know that we will just send this ping to see if the other end now is able to do things. Then we have here our send buffer from which we take packages on a timeout. Okay, we are missing one thing. We are missing the situation where we stopped putting packet, where we put more packages to our buffer than we can have en route, and then we will need somehow an additional call to send blocks. So we have send blocks only from try send, which we need somehow just call try send on a timer. Do we? I mean, try send is already triggered from the acknowledgement packages. So if we have more stuff on route, then it's fine. But let's assume that we send all the packages that we can. The other side filled up its buffer. We did not send any more packages. I'm somehow thinking that we can maneuver ourselves into a stale situation. I mean, whenever we do send, we try send. And whenever we have an egg package, we try send. Okay. Now that will be working because that will be working fine. Because the situation, if the receiving window is empty, sorry, 0, is that we run into this case. So we send an empty package and then we will receive an acknowledgement package on this empty thing. Process acknowledgement package with null, and then in the acknowledgement package we will try send. So it should work, and we should not maneuver ourselves into a situation where we cannot do anything anymore. Yep. That sounds reasonable. One thing that could be made more elegant would be if we somehow from the receiving side could decide to notify that our sending window is bigger. By the way, did we actually write that? We said that we need to divide this by package size, and also by segment size. Max segment size. Okay, but the thing is, this situation may here, while we get a window size non-zero, still end up with a window size of 0 if the window size was less than a package. But we can actually work around this. How can we do it efficiently? I mean, of course, the cheap way would be to take a modulo, and if it's greater than 0, then just add 1 or something like that. But let's try to be smart about it. We could do something like this. Window size plus segment size minus 1. And this should result in the division being always at least 1 unless the whole thing was 0. Because assuming window size is 1, then we already will get we forgot one. So assuming window size is really 1 byte, and we add 1 byte to segment size, we divide through segment size, then we already get one still, so we can send one more package. If window size is segment size minus 1, then the whole thing is segment size, 2 segment sizes minus 1. If we divide it by segment size, it still gives us 1. Yeah, this is this should work. And later we can change maybe to window size to actually be the buffer size and not because the way this would work now is that we would be in fact able to put into the buffer more than it was supposed to store. So we need to check whether it would actually drop a package in that scenario. So process block, we would drop a package. We would drop a package. We would drop a package, and buffer size would then become bigger than buffer count. So if we want the thing to operate this way, then what we would need to do is to change this check to if buffer size is greater than max buffer, then return. Because if it's not greater or equal, because there is no room. So if buffer size is greater or equal, then we cannot store anything into the buffer and we just discard the package. And if buffer size is less than max buffer size, then we can store something, and then we will just allow the buffer size to grow past the value that we set as a maximal limit. It's not the nicest thing. I will think about whether we will leave it like this or whether we change it to work with really transmitting as window size always the actual buffer size in bytes. Let's quickly check whether it works, and if it works, then we will be done for today anyways. And finally, you have some homework from this nice exciting project. Okay, it's working, despite the random package lost from time to time. So, any questions? No questions?
Actually, in the beginning, set up this. Okay, maybe where are we connected to? I forgot.
Okay.
Set up another virtual machine, did you?
No, I'm just running 2 threads in one process. So when we go to main, we start we start a client thread, a server process and a client process, and it's like just different threads in the same process. So like process, not process, but a procedure. So server procedure and client procedure, and the server procedure just here creates a socket, listens on port 1234, and then in the loop accepts all connections and creates a server procedure. A socket procedure, which then handles the server side of this connection for this socket. And in our client side, which is the client procedure, we just connect to localhost port 1234, send stuff, and then keep sending things. This way we can debug both ends of the connection in one Visual Studio. The other solution would be to just copy the project and run 2 Visual Studios at the same time, for example, and then debug on both ends. But this is more convenient, I think. And in principle, for what Windows cares, it does not really make a difference if we would be testing this into different threads or into different processes. So if we later implement some sort of benchmarking, connection speed test, etc., then the result should be the same whether both clients run on the same process or into different processes. It will only change once we would, as you say, put the other process on another virtual machine, because then we would no longer have a local host connection, but a remote connection.
Okay, thank you. This überblick die Fragen.
Okay, perfect. Any more questions? Okay, if there are no more questions, then that was for today. We'll see each other next week, and have a nice weekend. Bye bye.